Okay, the next topic is calculating gradients. Okay, I need to use my pen. Let's see what derivatives are first. This is kind of recap. A derivative of a function at any point tells us how much a minute increment to the argument or input of the function will increment the value of the function. So it means here we are at this position, and when we increment x, this small delta value, delta x, then how much the output will change. This is similar to delta y equals alpha times delta x. And here alpha is the derivative. It is the ratio. So alpha is the ratio between delta x and delta y. So when we change x a little bit, then how much y will change? And based on the fact that at a fine enough resolution, any smooth continuous function is locally linear at any point. As you can see here, we are taking an approximation. And as we make x go to 0, we can calculate the slope at this point, tangent. And here we are dealing with a scalar function of scalar arguments, meaning that the input x is scalar and the output is scalar as well. And the derivative is, as I told you, is alpha, the ratio between the increment of x and the increment of y, and often represented as dy and dx. Or alternately, we sometimes use f prime x to represent this value. So dy dx equals f prime x. They represent the same concept. And derivative f prime is the rate of change of the function at point x. How fast it increases with increasing x. And the magnitude of f prime x gives you the steepness of the curve at x. If the value is large, that means the function is increasing or decreasing more rapidly. It will be positive if f prime x is positive. And this means a small increment in x results in an increase of fx. However, if f prime, so this case, f prime x is larger than 0, f prime x smaller than 0, meaning that this value is negative. And when this value is negative, then a small increase in x results in a decrease of fx. And we say x is in the region of negative slope. And when f prime x is 0, then the function is locally flat. It does not increase nor decrease. So that is the meaning of derivative. And up to this point, we discussed a scalar function of scalar input. From now on, we're going to talk about multivariate scalar function, meaning that the output is going to be scalar. However, the input is going to be vector. Here, the notation has changed from scalar to vector. You can see this bold character. And what we want to get is alpha. Here alpha now becomes a row vector. And the total change of y is calculated by the dot product between alpha and delta x. Here, I'm emphasizing this fact again. The input x is now a vector. And let's say this x in the dimension of Rd. And the change of x, small change of x delta x, is now also a vector. So in the first dimension and dth dimension, like this. So here, alpha and x both are vectors. You need to keep that in mind. And here, alpha 1 means the rate of change in the first dimension, and alpha 2 is the rate of change in the second dimension, and alpha d, the rate of change in the dth dimension. And when we add up all these values, we can get total change of y. And this statement states that the partial derivative alpha sub I gives us how y increments when only xi is incrementing. And we saw this in the numerical gradient calculation session in the previous video. And this one is represented as partial derivative of y in respect of xi. And this one is alpha 1, this one, alpha 2, this one, alpha d. So now we are dealing with scalar function of vector arguments. Why do you care about this function? Because in our neural networks, we are going to input some images or sentences, and these are all tensors or numbers or vectors. They are not just scalar numbers. And after that, we calculate a loss, and this loss is just a single scalar. So that's why we care about scalar function of vector argument. In this diagram, you can see that when we change delta x, we want to get how much y changes. And we sometimes use this notation, this symbol. And this means taking gradient of y in respect of x. And we use this symbol for vector and matrix derivatives. And this one is defined as in the previous slide, taking gradient of y in respect of the first dimension and dth dimension. And this one is a derivative. And you may be more familiar with the term gradient, which is actually defined as the transpose of the derivative. So when you transpose this one, then that becomes gradient. Once again, the derivative of a scalar function fx, which takes multivariate input x, is a multiplicative factor that gives us the change in fx for tiny variation in x. So this is the derivative, and the gradient is the transpose of the derivative, and this one is the gradient. And as you can see here, this one is a row vector, and this gradient is column vector, because we transposed a row vector, and this becomes a column vector. And I talked about this quite a lot. This is a row vector, this is a column vector, and you can take an inner product. And by taking the inner product, you can calculate how much the resulting output changes. An inner product between two vectors of a fixed length is maximum when the two vectors are aligned, meaning that when theta is 0, the dot product between these two vectors becomes maximum. And in the previous slide, I mentioned that you can get the slope in any direction. Let's say here, you want to calculate the slope in this direction. Then what you do is you take dot product between these two vectors, this gradient, then you can get how much you increase or decrease the output value using the dot product between these two vectors. And this one is a direction vector. This is a unit direction vector. And by taking the dot product between these two vectors, you can get the magnitude of slope in this direction. And because the dot product between two vectors becomes maximum when they have 0 theta between the two vectors, the gradient is the direction of fastest increase in fx. Okay, so the function fx increases most rapidly if the input increment dx is exactly in the direction of the gradient. Pictorially, gradient vector looks like this. So it points one direction. And moving in this direction increases fx fastest. And by taking the negative direction, then you could decrease fx fastest. And what would you want to do when you want to decrease the loss function? We're going to take the direction of the negative gradient because we want to decrease the loss value. And at this point, gradient here is 0. Moving in any direction here results in no change in the loss function or the scalar function. Here, a small increment or decrement in the f value will result in no change in the resulting loss or the scalar function. And another property of gradient is that the gradient vector is perpendicular to the level curve. So here we have level curve containing the same values here, and gradient is perpendicular to this level curve. Okay, up to this point, we've discussed how we can calculate gradient. And now let's have a look at a concrete example. Let's say our function looks like this. It receives two values, meaning that the input is this vector, and the output is just one single number, meaning that it is a scalar. And how do we calculate the gradient? We first take derivative of f in respect of the first component, which is x. And next, we take another gradient of f in respect of y, the second element. And df dx is quite simple. We take these values, and here y is considered as a number, and we can remove this part, and only x is the variable, and x squared is derived as 2x. And when we take the gradient partial derivative of f in respect of y, here x is a constant, so y becomes 1, here y becomes 1. So the resulting partial derivative is x squared plus 1. And the gradient becomes, we collect these two results into xy, x squared plus 1. Quite easy. Okay, up to this point, we talked about calculating gradients. And sometimes we want to take the second derivative of a function f. Here we are still dealing with f, where the input is vector and the output is a scalar. And the first derivative was called gradient, and the second derivative is called Hessian. In this case, we are taking derivative of f in respect of x1 2 times. So first position takes the derivative of x in respect of 1 and 1. And the 1, 2 position takes derivative of x in respect of x1 and x2. Here, 2, n position, we're taking derivative of f in respect of x2 and xn. So we are just, although this matrix looks complicated, what we are doing is repeating this process in 2 directions. That's all. And so that's what we do to calculate Hessian. And there is another concept called Jacobian. Jacobian, in the case of Jacobian, the input is vector and the output is vector as well. And the first derivative of this type of functions is called Jacobian. Because we are putting a vector, the output is also a vector. And this one is one scalar, this one is another scalar. We have m scalar. And the Jacobian is nothing but the stacking of gradients. Here, we're taking the gradient of the first component, f1. And in the second row, we're taking the gradient of the second scalar. And we repeat this process for all the components. So Jacobian is like collection of gradients. And we represented them as a matrix. That's all. So this one is gradient of f1 and gradient of f2 and gradient of fn. Here we've discussed 3 concepts. You need to keep these in mind. The first one was gradient for f, where the input was vector and the output was scalar. And when we take second derivative, this one is first derivative, and when we take second derivative, it becomes Hessian. And when the function takes vector and outputs vector, we say the first derivative is Jacobian. So don't mix up these 3 concepts, and please keep these 3 concepts in mind. Although they look quite complicated, they are just the same thing. like taking partial derivatives in multiple dimensions or multiple directions. That's all. And this is our first question. Think about these two problems on your own after stopping the video and move on to the next part. Okay, have you finished solving these problems? Let's check the answer together. The first problem is select all that are true about derivatives of a scalar function f(x) of multivariate inputs. The first option says, at any location x, there may be many directions in which we can step, such that f(x) increases. I told you that we could take multiple directions like this, and we could calculate the magnitude of the slope by taking the dot product between these direction vectors with the gradient. And these directions also increase the value of the function, however, in different degrees. And the direction of the gradient is the direction in which the function increased fastest. That is the definition of gradient. And the gradient is the derivative of f(x) with respect to x. No, this is not true. I told you that gradient is the transpose of the derivative. And y f(x) is a scalar function of an n by 1 column vector. What is the shape of the derivative of y with respect to x? It is a row vector. Column vector, this is gradient. Okay, let's move on. The problem of optimization is to find the minimum or maximum values. And here is the definition of general formulation of optimization. Given a function, whether it receives vectors or scalar values, you want to find the value of x where f(x) is minimum. In this case, the minimum is achieved here. In this case, minimum is achieved when the input variable has this value. And in the scalar case, you can find the global minimum at this position. And how do you find the minimum of a function? You can find the value x at which f prime x is 0. Because at the minimum point, the derivative equals 0. And we're going to solve this equation to find candidate x values. The reason why I'm calling these values candidate is because the solution of this equation produces turning points. Derivative go from positive to negative or vice versa at this point. And it is not necessarily a minimum. And this is the second question I want to give you. Please think about it for a moment and move on. Okay, let's check the answer together. The answer is third one. For the minimum of a function f(x), f prime x becomes 0, and at the same time, the second derivative is positive. Why is it so? Both maxima and minima have 0 derivative, as you can see here. So the maximum, local minimum, they all have 0 derivatives. And these are called turning points. And when we plot the derivative, here, derivative is 0 for local maximum, and derivative is 0 at local minimum. So this line represents f(x), and this line represents f prime x. And as you can see here, both maxima and minima have zero derivative. And when we calculate the second derivative, because at this maximum point, derivative is decreasing, and the second derivative should have minus value. And here, at the minimum, the value is increasing. And the value is increasing. I mean, at the minimum point, the slope is increasing like this, from minus to plus. And as you can see here, because the first derivative is increasing, the second derivative should have plus value. So the solution of finding the minimum or maximum of a function is as follows. First of all, we find the value x at which f prime x equals 0. We're going to solve this problem, and the solution is a turning point. And the second process is you check the double derivative as solutions by computing the second derivative. And if this value is positive, then the solution is a minimum. Otherwise, meaning that if second derivative is negative, then it is maximum, as you saw in this slide. And a note on derivatives of function of single variable. All locations with zero derivatives are critical points. These can be local maxima or minima or inflection points. Therefore, you need to check the second derivatives. If it is positive, then it is minima. It is negative, then it is maxima. 0 means inflection points. And it is a little more complicated for functions of multiple variables. What about functions of multiple variables? The optimum point is still turning point, meaning that shifting in any direction will increase the value. For smooth functions, meaning you can derive the function at any point, at maximum or minimum, the gradient is 0, meaning that really tiny shifts will not change the function value. And how do we find the minimum of a scalar function of a multivariate input? The optimum point is a turning point, meaning that the gradient is going to be 0. Therefore, we are going to take the similar processes. We first find the location where the gradient is 0. So we are going to take gradient of f and then find the positions where the gradient becomes 0. And as we did for the scalar function of scalar input, we're going to calculate the Hessian matrix at the candidate solution. And if the Hessian is positive definite, or eigenvalues are positive, then we say this position is local minima. If the Hessian is negative definite, meaning that eigenvalues are negative, then these points are local maxima. And positive definite means for any matrix, if you calculate any vector multiplication between this matrix and input vector, if this multiplication is always larger than 0, then we say this matrix M is positive definite. If this multiplication is always smaller than 0, then we say this matrix M is negative definite. And if you put equal sign here, larger than 0 or equal to 0, then we say this matrix is positive, semi-definite. And in this case, if you put equal sign here, then we say negative semi-definite. This is just one property of a matrix. I'm going to give you a concrete example. Let's say our function looks like this. It receives a three-dimensional vector as input and outputs single number. And you can calculate the gradient like this. And before we move on, try to find the positions where the gradient becomes 0. That is our first step. All right, have you calculated the position where the gradient becomes 0? You can solve these problems by solving 3 equations, and you can get that when x is -1, -1, -1, the gradient is 0. Then we compute the Hessian matrix at that point. And the result is this one. And you can evaluate the eigenvalues of this Hessian matrix as follows. And because all these eigenvalues are positives, the Hessian matrix is positive definite. Therefore, we can say this point is a minimum. So this is the process of calculating or finding the minimum of a scalar function of multivariate input. However, the thing is, closed form solutions are not always available. Often, it is not possible to simply solve this function because we have 1 billion or 10 billion numbers of parameters. And maximizing or minimizing these big, huge networks is intractable. In this case, we use iterative solutions rather than analytical solutions. We start by a guess, and then refine this value over and over, and find correct values. And how do we find iterative solution? As I told you, we start from an initial guess, like x0, and update the guess towards better value of fx. By taking gradient, we know which direction we need to go. So here, by following the direction of gradient, we know where to move to decrease the value of the loss. However, the problem is we need to decide which direction to step in and how big must the steps be. That is the approach of gradient descent. We start at some point, we find the direction in which to shift to decrease the error. And if the derivative at the point is negative, then follow the direction. If it is positive, we follow the opposite direction. And this is a trivial algorithm. We initialize x, and while the derivative is not 0, if the sign is positive, then we take the negative direction. If it is negative, that means it is decreasing. So we're just following that direction. And we need to think about when we need to stop this iterative solution. There are many options. And we can condense this equation as this. We just follow sign or not. This is just simpler version of the previous algorithm. And we can determine the step size, how much we move. And this is another research area, how to determine the step size. Okay, this is the third fall. Try to think about this problem, solve it on your own, and check answers together. All right, have you solved this problem? Let's check this answer together. In fact, this is the question we solved previously. And this is just a reminder. At any location x, there may be many directions in which we can step, such that fx increases. There are multiple choices we can take. However, the direction of the gradient is the direction in which the function increases fastest. All right, this is kind of review. This is another recap. Gradient vector increases fx the fastest. And if you take the negative direction, then this function will decrease fastest. So that's why we care about gradients when we are updating or optimizing the values of our model parameters. And there is another algorithm called gradient ascent. The gradient descent and ascent method to find the minimum or maximum. Descent tries to find the minimum value and ascent tries to find the maximum value. To find the maximum, we move in the direction of the gradient. To find the minimum, we move exactly the opposite, the direction of the gradient. And as I told you, there are many solutions to choosing step size. And when do we need to stop our gradient descent or ascent? We say if the amount of update is less than epsilon1, this is a predefined value. We could just set it as 0.1 or 1 according to your application. So this is one criteria you can choose. Another option you can take is if the magnitude of our gradient is less than epsilon, this is also predefined, we just stop our iteration. And there might be many other options for stopping iteration. Over gradient descent algorithm looks like this. So we first initialize and then update our values over and over until this criterion is not satisfied. And for appropriate step size for convex functions, gradient descent will always find the minimum. However, for non-convex functions, it will find a local minimum or an inflection point. This is another problem. Try to think about it on your own. Okay, let's check the answer together. The answer is the third option. The problem was y is a scalar function of an n by n column vector variable. So the input is a vector, and starting from x0, in which direction must we move in the space of x to achieve the maximum decrease? So we want to get the maximum decrease direction. And I told you that direction of the gradient is the fastest increment, and exactly the opposite to the direction of the gradient results in the maximum decrease. And returning to our problem from our detour, our problem was this. Given a training set of input and output pairs, Here, X represents the input and D represent the expected output. In other words, we sometimes call it ground truth. And we want to minimize the following loss function. Here, our model is parameterized by W. And when we inject our input X, then there might be an output. And we want to decrease the gap between this predicted output, D hat, and the ground truth D. And this is a problem of function minimization, an instance of optimization. And gradient descent to train a network, what we are doing is as follows. We initialize the values of W, which is the parameter of our model. And we take gradient of the loss in respect of our parameters W. And then at each step, we're taking a step size and update our parameters using this equation. And we do this until the loss between the last step and the current step is larger than this predefined epsilon. We keep doing this. And at the end, we're going to be able to get the W values, which will minimize the loss, which is our goal. Okay, that was about gradient descent. And let's implement this concept to deepen our understanding. Okay, from now on, we're going to calculate gradients. The first function we're going to implement is numerical gradient with no patch. We're going to accept the function f and the input vector x. And we're going to set h as 10 to the minus 4. And gradients have the same shape as x. Therefore, we're going to create an array that has the same size as x, and we initialize the values as zeros. And what we are going to do is, for each index, or for each dimension, we're going to increment the value slightly meaning h. What we're going to do is calculate fx plus h, which is, and then fx h1 is going to be fx. The reason why we are taking this approach is because x is a multi-dimensional vector, and we're going to fix other values, but at each step, we're changing the value at the idx index. And next, we calculate x minus h, which is going to be temp value minus h. And then fxh2 is going to be just this value. And how can you calculate the gradient? fxh1 minus fxh2 divided by 2 times h. This is the same as how we calculated the derivative here. Okay, but we are repeating this process for each index. That's all. And we need to recover the value at the idx index. After all this, we return our gradient like this. And the thing is, because sometimes you use numerical gradients for multiple objects. To deal with that, we're going to implement this function as well. Here, we are using capital X to denote we are accepting multiple instances. If the dimension at the first position equals 1, meaning that we have only one data example, then we can use the numerical gradient no batch we just implemented like this. Otherwise, we're going to initialize grad as the shape of capital X. And we're going to loop over the dimension, each dimension and each item of X as follows, and calculate gradient. Like this. And after all, we return our gradient. So this is pretty simple to implement. And I'm going to show you an example. To do so, I'm going to implement an example function like this. Here, we're implementing a special function that receives two-dimensional vector like this. And it outputs x0 squared plus x1 squared. And if the dimension equals 1, we're going to just return x squared like this. Otherwise, we're going to return x squared following the axis 1. Okay, so this is a pretty simple function. And I'm going to show you and draw the gradient of this example function. First, we initialize x0 like this, and x1 like this. And we can create a mesh grid that relates x0 and x1. And because this vector and this variable is two-dimensional, and for computational efficiency, we are going to flatten capital X and capital Y like this. And we calculate gradient using our numerical gradient function. We put example function like this, and we pass our X and Y as an array. Okay, we calculated our gradient, and now let's visualize this gradient. To do so, we first make a figure using PLT. We import the plot. And here, I'm going to introduce a special method, quiver. Using this quiver, you can visualize gradients using arrows. And we are going to visualize the minus gradient, meaning that if we move following this direction, then we can reach the minimum value. I'm going to color the figure like this. I set the limit of x as -2 to 2 and y as 5. It's the same. And I'm going to add label like this. this. And I'm going to add grid, draw, and show like this. And as you can see here, I visualize the gradient. And if you move away from the center, 0.0, the gradients become bigger and bigger. And they all point to the same point, 0.0, because this is the minimum point. Okay? You can play around with numerical gradient function, implementing different functions. Okay. And now let's implement gradient descent. This function receives, of course, the function f and the initial position of x. So we are starting from this position in x and change or update this value to find the x that minimizes function x, function f. And here we are introducing LR, learning rate, and this is the step size. And we are going to receive the step number. How many times we are going to update this init x. So what we do is first initialize our x as the init x, and we save the x history in the list. And after that, we are going to visualize how x changed. And for I in range step number, we're going to conduct gradient descent. And before we do that, we copy x and append this value to x history. And this is going to be our first PPP exercise. And after all, we're going to return the final updated x and the history of x. Take some time and try implementing this gradient descent. You can use this numerical gradient here. All right. See you in the next video.